If you factor out the entire constant, then what you're left with should be what you proved in A.
He definitely goofed up on the contingency place. He said that he's only prorated us 11 points, but he prorated us
Are some of those from a paper assignment?
No, I actually told him. But he definitely, I mean, I'm not going to say anything because he helps us out.
Okay. I think last time I talked about a theorem which said F is closed if and only if every convergence sequence converges to a point in F, right? So today I want to start with another theorem. And this one says the following. So this one says that a subset is closed if and only if it contains all of its cluster points, okay? So a subset F of R is closed if and only if let's see, if and only if F contains all of its cluster points. Okay, so how do we prove this? This is a if and only if statement, right? So previously we showed that a subset is closed if and only if every convergence sequence in F converges to a point in F, right? Today what we have is F is closed if and only if it contains all of its cluster points. You guys remember what a cluster point is? X is a cluster point for F if every deleted neighborhood of X contains a point of F. Every deleted neighborhood of X. Remember, deleted neighborhood of X means a interval centered at X, excluding X. So every deleted neighborhood of X contains a point of F. That's what we mean by a cluster point. So what we are saying here, F is closed if and only if it contains all of its cluster points. So let's just go this way. Let's just assume that F is closed. Assume F is closed, and then I have to show F contains all of its cluster points. Okay, we have to show that F contains all of its cluster points. Okay, so how do we show that? Any ideas, anyone? So that is, if I pick a cluster point, I have to show that the cluster point belongs to F, right? So let's let X be a cluster point of F. Okay, the question to you is, how do you show that X belongs to F? How do you show X belongs to F? There are a couple of ways to go. There is one way you can directly show X belongs to F, or you can do a contradiction. Okay. Now, what is the meaning of F is closed? F closed means the complement of F is open, right? Now, X is a cluster point of F. Now, if I do a contradiction, right? So assume, so we need to show what? We need to show X belongs to F, right? So on the contrary, let's assume that X is not in F. So on the contrary, let me just say assume on the contrary, X is not in F. Well, then X will be in the complement of F, right? In the complement of F. Well, but the complement of F is open. Well, since it is open, there is a neighborhood of X which is inside of the complement as well, right? So if X is in the complement of F, then a neighborhood, then there exists a neighborhood, let's say, of size epsilon, so V epsilon of X, which is entirely contained in the complement of F. Is that making sense? Because the complement was open. Well, but X is a cluster point for F, right? So every neighborhood of X is supposed to contain a point of F, right? But there exists, so let's say there exists X epsilon in F such that X epsilon is in the neighborhood, epsilon neighborhood of X as well. All I'm trying to say is that the epsilon neighborhood of X must contain something from F, but we are saying that the epsilon neighborhood is entirely outside of F, right? So this is the contradiction. This is a contradiction. Is that making sense? Okay, so that's one way. That we assume that F is closed, and then we want to show that X is a cluster point. If X is a cluster point of F, then we want to show that X is inside of F. And we said assume on the contrary that X is not in F. Well, then a epsilon neighborhood of X will be outside of F for some epsilon. But that neighborhood should also include something from F because X is a cluster point. So that's where the contradiction is. Okay, now the other way. Let's now assume that F contains all of its cluster points and show that it is closed. So now assume. So assume F contains all of its cluster points if F contains all of its cluster points, we want to show that F is closed, right? We need to show F is closed. Okay, any ideas? What do I have to show that F is closed? Okay, so that is, we have to show, that is, we need to show the complement of F is open. Okay, so how do I show that? Anyone? Our assumption is that F contains all of its cluster points, and we want to show that the complement of F must be open. Anyone? You want to show that R/F is open. Okay. What would you need to show for that?
X in the complement,
Mhm.
there's a neighborhood.
Which is entirely there.
Yeah.
Mm-hmm. Well, let's think about the following. Okay, so as you said, let's let X be inside of this complement. Okay. And as Joanna, you told us that it means to show that the complement of F is open, we have to show that X has a neighborhood for any X, which is entirely outside of F, right? To show that R minus F is open. Well, why would that be the case? Well, X is in the complement of F. So what do we know about F? F contains all of its cluster points, right? Every cluster point of F is inside of F. So since X is not in F, X cannot be a cluster point, right? So by hypothesis, X is not a cluster point of F. Now, if X is not a cluster point of F, what is the meaning of that? Remember the definition of a cluster point. X is a cluster point means every deleted neighborhood of X contains something from F, right? So if X is not a cluster point, so what would that mean? It would mean that there's got to be a neighborhood of X which will not contain anything from F, right? If X is not a cluster. So there exists a neighborhood V epsilon of X which does not contain anything from F, right? So which intersected with F is got to be empty. or it means that V epsilon of x is inside of the complement of f. Let's see if you agree with that. If x is not a cluster point, that means that remember, cluster point means every deleted neighborhood of x contains something from f. If it is not a cluster point, then every neighborhood, right? Every neighborhood there's got to be a neighborhood which cannot intersect f. Well, that would mean that neighborhood should be outside of f, and that says that. But the neighborhood means an open interval, right? So that tells you that x is if x is in there, then a neighborhood of x is also there. Okay, is that clear to you? Okay, so that shows that. So we can say then that R slash f is open because we took x to be an arbitrary point there. So this is open. And that finishes the proof. Any questions, anyone? Any questions? All right, so let me move on to another theorem. This is an interesting theorem. What it says is the following. A subset of R, a subset of R is open. A subset of R is open if and only if it is the union, if and only if it is the union of countably many disjoint open intervals. So remember, open set means that if x, so we say that a set A is open if for every x in A, x has a neighborhood which is also in A, right? X has a neighborhood which is also in A. That's the meaning of open set. And we are saying that a subset of R is open if and only if it is the union of countably many disjoint open intervals. Okay? Now, one way is easy, right? Proof. Which way is easy? One way we already know. Which way is that? Remember last time I said the union of any collection of open sets is open. The union of any collection of open sets is open. Now open intervals are open sets, right? So the union of a countably many disjoint open intervals is of course open. So this way is done. So the way we have to the statement that we have to prove is the following: if A is a subset, A is an open subset of R, then A is the union of a countably many disjoint open intervals. That's what we have to show. So let's assume that A is an open subsets or is an open subset of R. Now I have to come up with disjoint open intervals, right? Disjoint open intervals whose union would be equal to A. Okay. Now, I really don't want to. So if you look at the proof in the book, it's probably a little. It's about a page. Okay, and I don't want to write down, detailed proof here, but I want to give you the big ideas in the proof. Okay, so what are the big ideas? The way you want to think about it is the following. Let for x in A, think about this. For x in A, note that I can think of the following. X is in A, x is open, right? Sorry, A is open. It means that there must be a neighborhood of x which is entirely contained. So there's got to be neighborhoods of x which are entirely contained in A, right? Well, let's just take, for any x, let's just take the largest possible open interval containing x that you can take. So see, if I have x, there is a neighborhood of x which is inside of A. But what I'm saying is that let's take the largest possible open interval containing x which is inside of A. The largest possible interval containing A which also contains x. Let's take that. I'm going to call that Ix. Okay. So that is, we can do that basically because we know that there is some neighborhood of x which is entirely contained in A, right? So there's got to be some number here, right? So maybe there are more than one neighborhood of x which are inside here, right? So you can take the largest possible right-hand point, let's call that bx, and you can take the smallest possible left-hand point, let's call that ax. Okay, so x is not necessarily the midpoint here. Okay, so the interval from ax to bx, I am going to call that ix. Ix is the open interval from ax to bx. Are you guys okay with that? So we are saying that for any x in A, let's define an interval, open interval, Ix, which is ax to bx, and ax to bx is the largest open interval inside of A containing x. Is that making sense? Now, what is basically bx? Bx is the supremum of, again, like I said, for any x, x has a neighborhood which is entirely contained in A, right? That means you have an interval like from here to here, right? And so there could be more than one neighborhood of x which is inside of A. So you basically take the supremum of the right-hand points of all the neighborhoods of x which are in A, and also you want to take the infimum of all the left-hand points of the neighborhoods of x which are inside of A. And that way you get ax and bx. So ax and bx are the supremum and infimum. Is that making sense? So maybe I should write that down. So what is ax? Ax is the infimum of all the numbers A such that the interval from A to x is entirely contained in A. And bx is the supremum of all the numbers B such that the interval from x to B is entirely contained in A. Is that making sense? Any questions on that? Now you might say, hey, how do I know supremum and infimum occurs? Actually, I don't know. So what I should be saying is that maybe there is no supremum for this set B. Set of all B such that xB is inside of B, there is no supremum. That means that's an unbounded set. In that case, you take Bx to be infinity. Same way, if the set of all A is such that Ax is inside of A, if that set has no lower bound, okay, it has no lower bound, then you say that let's take ax to be the negative infinity. So ax could be either this or negative infinity, and this could be this or positive infinity. Okay, but still it's an open interval. Now, is it clear to you that if I define for any x in A, if I define Ix to be an interval like this, then isn't that clear that now I could say that the set A would be the union of all these Ix, where x goes over all the numbers in A. That should be clear because for every x in A, I have Ix, right? So x is contained in Ix. I'm taking the union of all these intervals, and it's gotta be the same as A, right? For every x in A, I have Ix. Ix contains x, right? So that's clearly every x in A is inside of some Ix. So the union of Ix covers everything in A, right? So A is the union of Ix. So we already showed that A is the union of open intervals, right? But what do I have to show though? I have to show that A is the union of countably many disjoint, right? Open intervals. So all I have to do now is show to you why can we make it countable, and why are they disjoint? Okay. So here's how we could do it. Here's how I would think about it. Let's take the rational numbers. The rational numbers, let's take an enumeration of that. By that I mean, remember, the set of rational numbers, that's a denumerable set, right? It means there is a one-to-one correspondence between Q and N, right? So let's enumerate the rational numbers as R1, R2, R3, Rn, and so on. So this is a one-to-one correspondence between the counting numbers and the rational numbers. Okay. Now, for let's do the following. Okay. For any x in A, Ix is an interval, so it contains rational numbers, right? By the density theorem, it's got to contain rational numbers. Let's take the rational number with the smallest subscript from this enumeration that is inside of Ix. So for any x in A, let n be the list so that Rn belongs to A. Does that make sense? N is the smallest subscript. You see, for any, not in A, sorry, not in A, Ix. For any x, Ix is an open interval, so it has rational numbers. So among those rational numbers, I am picking the one with the smallest subscript. Okay, because I already assigned this subscript to all the rational numbers. Now I claim that Ix is exactly the same as let me call that Rnx, okay? Irnx. Okay. Nx is just a, Nx is, let me call that Nx here. Nx is just a counting number. So what we are saying is that Ix and Irnx are the same. Okay, for each x, you could do that. Now, there could be two different x and y. Okay, there could be two values of x, okay, for which you get the same Rnx. Is that making sense? But this is giving us modulo the fact that I have to show you why these are equal, then what you have is that for any x in A, Ix2, you have a mapping from the set of the set of intervals Ix into the set of intervals where the subscripts are R and X, right? So you have, so this gives you a correspondence. But if you look at I, R, and X, right? The intervals of the form I, R, and X, that's the set of all intervals, that's a countable set, right? So note that if I look at the set of all I, R, and X, such that, let me just say this. If I just look at this set, this is a countable set. Is that not correct? Because the subscripts are going by this R and X, right? These are the rational numbers, and there are countably many of them. Okay. Now, the point though here that I have to know here is why is Ix the same as I, R, and X, right? Why is that true? So think about it this way. Here you have the interval, and here you have X, and here you have AX. Maybe let's say BX is here, right? See, R and X is a rational number also, which is inside of A, right? Which is inside of, in fact, IX, which is a subset of A, right? Sorry, yes, R and X. Remember, the way we picked R and X was that it's a rational number inside of the interval Ix, and it's the one with the smallest subscript. So I know that R and X is inside of this interval, right? Inside of this interval, maybe right here is where R and X is. Now, how do I know that I subscript X, that set, which is from AX to BX, which is from AX to BX, why is it the same as I, R, and X, which would basically be A, R, N, X to B, R, N, X. Maybe I shouldn't have used too many subscripts here. Okay. Why are they equal? Well, if they are not equal, right, what could happen, for example? If they are not equal, right, if Ix and I are n x, remember R and X is also in Ix. If they are not equal, what could go wrong? Maybe BR and X is bigger than BX, right? That could happen, BR and X. But is that possible? Would that be possible that BR and X is bigger than that? The reason is, you see, remember, for each x, we picked AX to BX to be the largest interval inside of A containing X, right? So if BR and X was bigger, then I could have extended that to AX to BR and X, right? Same way, BR and X cannot be less than BX, because if you say, okay, say BR and X is right in here, if you say that, well, then you can look at this guy and say, this is the largest interval which contains R and X, but then you have this BX bigger than that. So now you have a bigger interval containing R and X. Is that making sense? So that's why we could say that IX and IR and X, they are the same intervals. Okay? So the mapping that I have here was a mapping from the set of all Ix into the set of all I, R, and X. And since it's a I shouldn't say it's a one-to-one mapping, okay? Because you know, for two different, so if I have, there might be there might be two numbers x and y such that ix and iy are the same. And in fact, that happens when x and y are both in ix, okay? So if I pick any xy in A, okay, what happens is that either these two are equal or ix intersected with iy is empty. Okay? So for any xy in A, ix is equal to iy or ix intersect iy is empty. Now because of that, the mapping that I have here, what can I say about that mapping? It would be an onto mapping, but the deal is it's an onto mapping, but the way we picked IR and X, the IR and X, this set here, okay? This set is it, so from the set of IX into the set of IR and X, this is a onto mapping. But now look at the fact that the union of IX will in fact be the same as the union of IR and X. Okay? And because of that, now I have a disjoint union of open intervals, countably many also. So you see the part where the part to show that A is the union of open intervals is easy. You just, for any x, you just take the largest interval inside of A containing x, and then this Ix will cover all of A. So it's easy to write A as a union of open intervals. The question is, how do you write it as a union of countably many disjoint intervals? Okay? And to do that, what we said is the following. Now, maybe I should go back a little bit. I feel like, how many of you feel comfortable with what we did so far? Feel free to say that you're not clear, okay? All right. So let's go over this a little bit more, okay? So here's first of all, let's understand what did we mean by AX and BX. A is an open set. It means that for every x, there is an open interval, right, containing x, which is also inside of A. That's what it means that A is open and X is in A. So what I'm saying is that for any x, let's take AX and BX in such a way so that, well, let's take IX to be the largest possible open interval inside of A which contains X. Which basically means the following. I am taking AX to be the infimum of all A such that the interval from A to X is inside of A. Okay? And in fact, I could have said, you know, closed interval right here because X is in A. I could have said closed here also. And Bx I'm taking to be the supremum of all B such that the interval from X to B is inside of A. There are such B and A because there is an open interval containing X like that, right? And you're taking infimum and supremum of these two sets as AX and BX. Now you might say, hey, the set of all B such that the interval from X to B is inside of A, that might not be bounded above, right? It might not have an upper bound. In that case, I'm going to take Bx to be infinity. Same way, if I don't have an infimum for the set of all A such that A to X is inside of A, then I would take the infimum to be negative infinity. Okay, so Ix, so here Ax and Bx could be Ax and Bx that I have, they could be positive or negative infinity. Is that making sense? Are you guys clear on the meaning of Ax and Bx? Mm-hmm. Okay, so once I have this Ax and Bx as Ix, then it's clear, right, that A is the union of all these Ix's, right? A is the union of all these Ix's. All right, if that's clear to you, now let's see. So let me make a break here and let me redo the next stuff that I have. So let's think about this. Suppose I have two numbers, x and y. Both of them are in A, right? How are Ix and Iy related? How are Ix and Iy related? So here is my, say, Ax and Bx. Sorry. And maybe X is somewhere here. And then suppose, so there are two cases. So this is Ix, right? From here to here, that's Ix. So when I have X and Y, there are two cases. Maybe Y is inside of Ix, or Y is not inside of Ix, right? So the question is, what I want to show is that there are two possibilities. Ix is the same as Iy. That's one possibility. Or Ix and Iy, they don't intersect at all. These are the only two possibilities, right? Why is that? For example, like I said, if suppose you're thinking of Y being here, okay? Y being here. Okay. So for Y, you have, I claim that if Y is in Ix, right? If Y is in Ix, then Ix and Iy are in fact the same. If Y, so this is what I'm saying. If Y is inside of Ix, then Ix and Iy must be the same. Why is that? Well, suppose you think that maybe By is bigger. Okay? I'm not giving you a detailed proof here, but I'm saying what can go wrong. If you think that By is bigger than Bx, I don't care right now what is Ax, Ay. Well, that's a problem, because that would mean that I have an interval from Ax to By entirely inside of A, which contains X, but I took Bx to be the largest possible like that. Right? So By couldn't possibly be bigger than Bx. Same way, By cannot be smaller than Bx. Otherwise, you can extend the Iy into something bigger. So you can argue same way what happens when Ay is smaller than Ax, Ay is bigger than Ax. Okay? Same way you can argue that that cannot be the case. So what you want to argue is that Ax must, if Y is in Ix, then Ax and Ay, Bx and By are the same, and so Ix and Iy must be the same. Okay, once again, I'm not giving you the details here. Now, so that's what we're saying. If Y is in Ix, then Ix and Iy must be the same. Okay. Similarly, you can argue that if Y is not in Ix, then Ix intersected with Iy, they are distinct. I mean, they don't intersect. The argument is very similar. So you're gonna, if you think that there is an intersection, then again, because of the way you defined Ax and Bx as infimum and supremum, it's going to contradict that idea. So that's why you can't have them to be intersecting unless Y is already inside of Ix. So you should disjoin. Yeah, they are disjoint if Y is not in Ix. So the only way Ix and Iy have intersect is when they are actually the same. Then I said, okay, here is one of the argument. I want to show that I have this set of all. So right now I have the set of all Ix, right? That might not be a countable collection, and as you saw that this set of Ix, they are not all different, right? Because there might be, once I find Ix, now for any Y in Ix, Iy is also the same as Ix, right? So I don't know if Ix's are countable. I also don't know whether they are disjoint. In fact, they are not disjoint, because if Y is in Ix, then Iy and Ix are the same. So I want to now come up with a disjoint countable set of disjoint intervals, right? So what I'm saying, well, each Ix must contain some rational numbers, right? By density theorem, any interval has rational numbers, right? And I'm saying let's enumerate the rational numbers as R1, R2, R3, R4, and so on. So this is an enumeration of all the rational numbers. So given a specific Ix, right? Given a specific Ix, there are many rational numbers in it, but I am picking the one with the smallest index, n. I'm calling that nx. So nx is the smallest index for which the rational number Rnx is inside of Ix. So then what happens is that since Rnx is inside of Ix, then I, Rnx, and Ix are the same, right? So for each Ix is the same as I, Rnx, right? And in fact, it's going to work for any x in A. Well, then what I'm saying is that the union of I, Rnx is the same as the union of all Ix, but that is equal to A. But the union of I, Rnx, that's a countable collection. That's a countable collection. But you also have to justify that the I, Rnx's, they are all disjoint. How do you know they are all disjoint? That's one more thing that you have to establish. Is that making sense? Why they are disjoint? Because the way we picked nx, we picked nx to be the smallest index, and what you want to argue is that suppose I, Rnx is the same as another I, Rny. Intersection is not empty. Well then, that's going to contradict the fact that nx and ny are the smallest indices. Okay. Again, I don't want to give you you don't have to worry about the details here. You have to remember though the fact that a subset of R is open if and only if it is the union of countably many disjoint open intervals. Okay. That's a very nice fact. Let's see if you have any specific questions, okay? The best thing to do is really ask me what questions you have on this. Again, this is a very subtle proof. It's not an easy proof. Like I said, it's one whole page in the book, okay? It's not a small proof. All I tried to do is give you the big idea. Why this is true. I didn't try to give you the details. Any questions? Any details that you didn't understand or you want more details? Maybe I should have done it before.
About 80%.
Yeah.
Well, go ahead and say that, okay, this part that you said is not clear to me.
I did where the Ix equals the Iy. We did that part. And then we wanted to show that if they're not the same, then they're disjoint. But
Yeah, so either they are the same. The statement is either Ix is Iy or Ix intersected with Iy is M. So what we said is that so for any, this would be for any xy inside of it. That's the case. All right. So assume. So I told you when this is the case. Okay. If x and if I have Ix and then if y is also in Ix, they have to be the same. Okay. Now, if I want to prove this statement, what do I have to prove? Either this or this, right? So if this does not happen, then I have to show this happens. So suppose that Ix is not equal to Iy, okay, Ix and Iy are not equal, then I have to show that this happens, that their intersection is empty. Why would that be the case? Think about the picture I gave you, right? We're thinking about some Ax, you have x, you have bx, right?
Right.
And then you have, we are saying Ix and Iy, they are different. If they are different,
So y is outside of AX and BX?
yeah, so if they are different, so I already argued that if y is inside of Ix, then they are the same. So
Understood.
y cannot be inside here. So y has to be somewhere outside. Maybe y is here. Okay? Now I am picking now we are picking an interval for y, right? So the question is the interval that I pick, maybe ay, do you think ay is something like this, and by is something like this? Right? The question is, does the interval for y intersect the interval for x, right? So the question is, why can't this happen if they intersect?
Because then we could just make the interval AX to be what?
Exactly. The problem is, if I think that maybe the Iy looks like this. Iy is from here to here, and Ix from here to here, right? Then what can go wrong? Well, then as Tommy said, well, then I have the interval from Ax all the way up to by. That's an interval inside of A. But that contradicts the fact that Ix was the biggest interval containing x, right?
By becomes the supreme.
Yeah. So it's not really hard, but it's just a matter of thinking the right way. It all depends on the way we pick Ix and Bx. I think this is a remarkable proof. It's just a matter of, you see, all you did really was choosing Ax and Bx, right, in a nice way, and then everything works. Everything works because of the way you defined Ax and Bx. Is that making sense?
Yeah.
Okay, so that's why the intersection has to be empty. Okay. And I guess once you know that, then the other things are clear, right? Because if I said Ix is the same as I, R, and X, and that's because this guy was chosen to be inside of Ix, right? I chose this guy to be a rational number inside of Ix. So they are equal, we know that. And I think the last thing we needed to understand was, why is this a disjoint set, right? Why, this is accountable clearly because R and X, these are rational numbers. So this is a countable set. Why are they disjoint though? Why are they disjoint? Well, because, remember, if they are not, if this is not a disjoint collection, right? If you say, then two of them must be the same, right? Then you would have to say that, okay, I, R, and X must be equal to I, R, and something else. Okay? But if they are equal, right? If they are equal, then what would that mean? These two guys must be the same rational numbers.
Actually, otherwise
Because we
same
picked
index.
them to be the smallest index, right? The smallest possible. So that contradicts. So that's why, if they are the same, then the indices must be the same. So that means this is a disjoint collection also. Okay. In any case, look into this from the book again and see if it makes sense, okay? And if you have more questions, you can ask me next time. So I thought by showing you the big ideas, I'm going to save time, but actually I didn't save time. So.